Your heart beats about 100,000 times every single day. It's this steady, reliable rhythm that we all just take for granted. But what happens when the electrical system that drives that beat starts to fail? Well, it's a biological glitch with a truly brilliant technological fix. So let's dive into this incredible intersection of biology and engineering. What you're looking at here is the fundamental pulse of our existence. Every single peak and valley on that screen tells a story. But when that story gets disrupted, when that rhythm falters, it can be life-threatening. And the cause, believe it or not, often lies in a tiny specialized piece of tissue.
Okay, so let's meet the sinoatrial node, or the SA node for short. The easiest way to think about it is as the heart's own biological spark plug. It's located up in the right atrium, and its whole job is to send out a consistent electrical pulse that tells the rest of the heart muscle, okay, time to contract. It's basically the master conductor of your own personal orchestra.
But here's where the trouble starts. Sometimes that signal from the SA node just gets weak, or maybe it becomes unreliable, or it even gets blocked on its way to the rest of the heart. The result? A big drop in heart rate, a serious disruption of that vital rhythm, and that can have some really serious consequences. So that brings up a huge engineering question, right? If the body's own electrical system is failing, can we actually build a better one to support it? And the answer, of course, is a resounding yes. And here it is. This is the solution, the artificial cardiac pacemaker. It's this small electronic device that's surgically placed right under the skin, and it's designed to do one thing: take over the job of that failing SA node and send those life-sustaining electrical impulses straight to the heart. When you break it down, the device is actually elegantly simple. It's really just two main parts. First, you've got the pulse generator. That's the brain of the whole operation, creating the electrical signals. And second, you have the lead. Think of it as the messenger. It's an insulated wire that carries those signals from the generator directly into the heart muscle itself.
But not every heart rhythm problem is a permanent thing. Sometimes after something like a heart attack or a big surgery, the heart just needs a little temporary support while it heals. And to deal with that, engineers came up with two pretty different approaches to pacing. So on one hand, you've got external pacemakers. These are for short-term emergency situations, after a major surgery or during a cardiac standstill. The electrodes are just placed right on the skin. And on the other hand, you have the implantable pacemakers we saw earlier. Those are the long-term solution for chronic or permanent heart rhythm problems.
Now, the very first pacemakers were basically just a metronome for the heart. They were super straightforward devices. They had one job, and one job only: deliver an electrical pulse at a constant fixed rate, let's say 70 beats per minute, no matter what the heart itself was actually doing.
But hang on a second, that raises a really interesting question. What if the patient's own heart is still trying to beat on its own? What if it only needs help every now and then? Firing a constant signal could actually end up competing with the heart's natural rhythm. That's a problem.
And that is the moment pacemakers got smart. The original fixed-rate models just fired away constantly. But the major leap forward, the real game changer, was the demand pacemaker. This new device could actually sense the heart's own electrical activity. It listens, and it only steps in to send a pulse if the heart's natural rate drops too low. It works with the heart, not against it.
So, with all this new complexity, pacing different chambers, sensing different signals, responding in different ways, you can imagine the confusion, right? Doctors and engineers desperately needed a standardized language, a universal way to describe exactly what each one of these devices was programmed to do.
So they created this, the pacemaker code. Now, I know what you're thinking. This table looks a little intense, but I promise you the logic behind it is actually pretty simple. It's a code, usually just 3 letters, that tells you everything you need to know about the pacemaker's basic function. Let's break down a really common example to see exactly how it works.
Okay, so let's jump right in and decode one of the most widely used pacemaker settings out there, VVI. Once you understand these 3 letters, you'll really get the core logic of how these modern pacemakers think.
All right, let's break it down. The first letter, V, tells us which chamber is being paced. So V stands for ventricle. Simple enough. The second letter, also a V, tells us which chamber is being sensed. And again, it's the ventricle. Now, the third letter, I. This is the most important one. It tells us the response. I stands for inhibited. What that means is, if the pacemaker senses a natural heartbeat in the ventricle, its own output is inhibited. It just holds back and does nothing.
So, the crucial point here, the big takeaway, is that a VVI pacemaker isn't running all the time. It's like a vigilant, on-demand backup generator for your heart. It's constantly monitoring the ventricle, and only when it senses a pause or a missed beat does it step in to provide that life-saving pulse. It's elegant, it's efficient, and it's perfectly in sync with what the body actually needs.
So we've gone from these simple little metronomes to intelligent devices that can literally listen and respond to the heart's most subtle signals. It really makes you wonder, doesn't it? With technology getting smaller and smarter and more integrated with our own biology, what's the next frontier for the devices that can literally mend a broken heart?